Hello everyone, so today in this video we're going to be cover a question which is related with the continuously stirred tank reactor. So as we previously looked to the questions that are related with the material balance, in this question we're going to work with both material and energy balances. So as we are going to be working with a continuously stirred tank reactor, let's just draw the diagram for our reactor first. So we're gonna have our reactor, and as it's continuously stirred, there's gonna be kind of something like a propeller that's gonna stir it all the time, and we're gonna have a cooling jacket with the cold water. So we don't know about if the reaction is going to be exothermic or endothermic. So this cooling jacket is going to provide for our controlling the temperature. So in this question here in the below the question, we're provided with some variables, right, parameters. And so let's go through these parameters first. So we have Q, and the value for Q is 100 liters per minute. So we know that it's going to be our flow. So as we are given only one flow, the flow that's going in and going out is going to be the same. So, and we also have a concentration of AI, but we don't know if it is we have an I, but we don't know if it's initial but or that's coming in. And here, if we look at this part, we have some values with zeros, right? So these values are going to be our initial values. So our CAI constant is going to be our concentration of A that is coming in. So we're going to have a reaction in our reactor, which is A is being converted to B. So that's going to be the concentration of A that's coming in. And then here we have our tau, but if you look at the value, it is Kelvin, right? So it's kind of strange that we have our tau as Kelvin. So it must be the typo here. So this must be actually the capital T, which is going to be our temperature. So it's going to be the temperature, as we also have I and 0 here, and we have also 0, 1 here. So which means Ti is going to be our temperature that's coming in, and and then our T0 is going to be our initial temperature. And then, so we have our volume, right? So as we're only provided with one volume, which means it's going to be a constant volume problem. So the volume is not going to change. So the volume of things inside of a reactor are going to be conserved. And then we have our rho, which is going to be the density of a product here inside. We have our C with the unit joules over grams times kilogram times Kelvin, right? So which is going to be our heat constant. And then we have our HR. We know that delta HR is our rate of reaction, right? And if we look at this, it is negative delta HR. And we have a positive value here, which means our reaction is exothermic. So some of energy, heat is going to be produced during the reaction. So the reason because of the cooling jacket is going to be towards kind of maintaining the same temperature because of the exothermic reaction. So it's going to cool down the reactor as the reaction goes. And here we have E over R thing. Okay, so we have our Arrhenius equation. It is defined as K is equal to K naught times E to the E negative EA over RT, where our EA is the activation energy and R is the constant and T is our temperature. And Q naught is the provided constant. So here we have our K naught here, right? It's 10.2 times 10 to the 1 over minutes, right? And so this is going to mean the constant at which our molecules are interacting with each other. So when the heat energy is, when the temperature is too big, it's going to be equal to, so when at a very high temperature, our rate in which the collisions are occurring is going to be equal to the maximum number of the collisions. Okay, so this is our Arrhenius equation, and this E over R represents this part of our equation. And here we have UA. So it is going to be the energy in a specific area. We're going to go that later. And we have our three variables, three initial variables. So Tc naught is going to be our initial cooling temperature for the cooling jacket. And Ca is going to be the initial concentration inside of a reactor. And T naught is going to be our initial temperature. So if we look at the question, here it says that we have a first order reaction, A is being converted to B, which means our rate of reaction is going to be equal to K, which is determined from Arrhenius equation, times the concentration of A, right? So it's going to be K times Ca, because as it's the first order reaction, we don't have any power to the concentration of A. And here it says the two state variables of ordinary differential equations are the concentration of A, which is going to be Ca, and the reactor temperature. So which means we are going to be needing two differential equations to solve this, to kind of simulate this question, this concept using the Python. So we're going to have two ordinary differential equations, one with the rate in which the concentration of A is changing, right? dC and d concentration A over time. And the second one is going to be the rate of change of a temperature, right? So we should have two things which is going to be equal to this. So we should determine the right hand sides. Okay, let's just first we can erase this for now, and let's just work with the flow things and determine our first ordinary differential equations. So as we know, in our questions related to flow, we have something that can be applied to everything. So we have the rate of change of a mass of a reactant is going to be equal to the rate of change, which is the reactant is coming in minus the product is going out of the reactor. And as we have our reaction A is being converted to B, we're gonna also have to divide the A that is being converted to B. So A consumed, right? So we'll be working with this concept to represent our differential equation. So we have our rate of change of the concentration. So we can multiply this by volume and try to set up this side. And because this is going to be equal to the flow rate times the concentration, right? Because here we have our concentration times volume over time, right? And so our unit for Q is volume over time, which is going to make the same thing. So for this side, we're going to have our flow times the concentration of A that's coming in. And as we have our constant flow, so the flow is not changing, so the flow coming in is equal to the flow going out of the reactor. We're going to just divide it, the concentration of A that's going out, which is going to be equal to the concentration of A inside of the reactor, as stated in the question. So because we're only given a CA, and we're not given kind of CA that's going out of the reactor, so we're going to say that it's going to be equal. So that as the flow is going to be equal the same when it's going in and going out, I can write this down in this form. And we also have to work with the A, the A which is going to be consumed because of the reaction. So I'm going to say that we know that our rate of the reaction is going to be equal to this thing, right? So I'm going to just get that. So K times concentration of A, right? And I can just multiply it by volume because of the units, because we're trying to find the material, the mass that is being the rate of change. And so if we try to divide both sides by a volume, we can have something like this, because in order to apply our solve IVP function using Python code, we must have our rate of change equal to something, equal to the right hand side. But as we have our volume on this side, we should get rid of it. So because of that, we can divide it by volume. So we can have Q over V CAN minus CA minus KCA, right? So this is going to be equal to our first ordinary differential equation. So now let's get to the second one. So as we dealt with the material, now let's try to work with the energy stuff so that we can find out the rate of change of temperature. And we know that as we have our reaction, the enthalpies are kind of must be conserved, so that we can set up the differential equation so that that can work with the enthalpy. So there is an enthalpy that's going into the reactor, right? And that is the enthalpy of product that's going out of the reactor. And we also have our kind of energy that's being used for the reaction, right? And that thing is going to be equal. So here we had our UA, right? So for that thing, we can represent our Q that's going to the energy. So the reaction thing is going to be the enthalpy, right? So because of the energy, we're going to have the rate, the enthalpy of reactants and enthalpy of products. But this thing, UA, is going to be because of the cooling jacket. So it's going to be the cooling jacket, the change of temperature across the area of the reactors. So we can represent the energy that's being that's getting to the cooling jacket as Q equals UA times the change in temperature, right? So we can get this and we can just plug it in here. So it's going to be UA and change in temperature with the reactor and cooling jacket. And so we're done with this side now, but let's try to work with this side for a bit. Okay, we know that our dt over T is gonna be, the units is gonna be kelvins over minutes, right? But for this side, we have our UA. So the unit for UA is joules per minutes times Kelvin, right? Joules per minutes times Kelvin. No, it was the Kelvin denominator, sorry. So it's going to be Kelvin, right? And it is multiplied by kelvins which is the temperature. So they're going to cancel out, so we'll be left with the joules over minutes. So here, which means for this side, we should also get the same thing. So we can, for that thing, we have our, here we have our heat constant, which has the unit joules over grams times Kelvin, right? So it's going to be joules over grams times Kelvin. And if we multiply this by the density and volume, so it's going to be liters times grams over liters, we can get rid of this, this, and this. So in both sides, we're going to have a unit of joules per minute. So the rate of change of energy. So which means we should multiply this sides by rho times volume times heat constant. And that's going to be our second differential equation. But let's try to work on it a bit. Let's try to manipulate it so that we can have something that we can apply to the Python code. So for the change of enthalpies, okay, what we can do is the enthalpy that's going in. So let's just write this side first. C times dt, rate of change of temperature times. So there's an enthalpy that's going in to the in, right? So which is gonna be dependent to the flow and the heat constant. Okay, so we can set up it as Q times rho times C, and with the change in temperature. So it's flow, which is being kind of multiplied by the density times the heat, our heat constant, which is kind of constant for our reactor, and that's going to be the enthalpy that's going into the reactor. And for this thing that's going out of the reactor, so as we have our reaction from A to B, and we're also given the enthalpy of reaction, right? We're given the negative delta HR, so enthalpy of the reaction. So we're gonna have, we can write this down as negative delta HR, negative delta HR. So it's the enthalpy, right? We can just multiply this by volume times the rate of reaction, because it is the reaction being it's the reaction, so it doesn't depend on the flow, it depends on the rate of reaction. So our rate of reaction is going to be KCA, and we can just write this down to continue our equation. So I'm just gonna write this below. So now we have something that can be used with the Python. But again, if we try to use solve IVP, we should have our rate of change of something equal to right hand side. So we're gonna divide everything by density times volume times heat constant, so that we have rate of change of temperature equals to a right hand side. So let's just write this down, our final differential equation. So it's going to be rho is going to cancel and heat constant is going to cancel, so it's going to be Q over V and change in temperature, right? Minus, if I'm going to divide this, it's going to be negative delta HR times the volume is going to cancel, KCA over rho C, right? Density times heat constant. And I'm going to divide this side by rho Vc. So it's going to be, so now here we have our final ordinary differential equation in respect to the energy balance that we can apply to Python code, use solve IVP, and we can use these two ordinary differential equations to actually simulate our reaction, our problem, which is dependent to the continuously stirred tank reactor. Okay, so now we'll be working with the code and see what happens. Okay, so now let's just try to write the Python code that will simulate our equation and try to see what kind of model we're going to have using our ordinary differential equations we found earlier. So for our code, as we are dealing with differential equations, we're going to be using solve IVP function from SciPy integrate. So we're going to get our usual imports, that's our NumPy, SciPy integrate, and we're going to get our plotly. So because we have to plot our model, and we usually have our plotly in dark mode, so it just makes our plotly dark, our graph dark in dark mode. Okay, so for starting the coding, we hear from the question, we here notice that there are two cases that we have to see where the cooling temperature goes from 300 to 290, and the second case is where it goes from 300 to 305. So there are going to be two different plots. We're going to see two different cases. So let's start from the first case where our cooling temperature on a cooling jacket goes from 300 to 290. Okay, for our code, we need to have our these constants in our code, right? So we're going to be using them. So let's just get them all here. Okay, so we need our Q. So our Q is going to be equal to 100, right? And I'm going to use dots because I just want to make sure that it's going to be like our Python is going to get it as float, not an integer. Okay, so we have concentration of A that's going inside. I'm going to make it CAN. So it's going to be 1, right? Okay. And we have our temperature, right? Which is going in. So it's going to be 10, it's going to be 350 dot. And I'm not inputting the units because we already have that in the question, but we can input them like as and comment them so that they are not a part of our code. Okay, so then our next value is gonna be our volume, which is 100 liters, right? And then we need our rho, which is equal to 1000. And the next one is the heat capacity. I'm just gonna make it equal to C. It's gonna be 0.239. And the next one is our rate of energy and enthalpy of our reaction. So it's gonna be, I'm just gonna make it HR, okay, and I'm gonna make it 5 to the 4th, 5e to the 4th. Okay, then what else we have? We have ER, right? EOR. I can just make it ER. Okay, so let's have it as 850, right? And then what else do we have? We have our K naught. It's going to be equal to 7.2. And what is that? Times e to the 10, right? And what else do we have? We have UA. it's going to be equal to 5 multiplied by 10 raised to the power 4. Sorry. And the next, also we also have our initial values, right? We have T cooling temperature naught, which is going to be equal to 300. And we also have our concentration of A naught, which is going to be 0.5. And we have our temperature inside of a reactor naught, which is equal to 350. And oops. What else do we have? So we know that we're working with the first case, so our ending cooling temperature is gonna be 290, right? So we're gonna make that Tc is equal to 290. And we're also, as we're gonna be running, it's a differential equation, we will need to supply our work with the time, so we will need to set a ending time. Okay, let's just have our ending time to be equal to 100. Okay, that must 100 minutes. That must be enough, more than enough. Okay, I'm gonna have all the constants. Okay, now we said that as we're working with the differential equations, we will need to work with the solve IVP function. But in order to use solve IVP, we need to have a function which is going to be our right-hand side. So let's just define the function, which is right-hand side, which is going to be taken. So our right-hand side function usually takes the time, right? The variable, dependent variable. So it's going to be our time, and it should get a vector. So we're going to unpack our vectors as our concentration of A and T, because they are two values that we have our ordinary equations. Okay, we can make this function and return our differential equations, but before that we are using our k values inside of our differential equations, but we have to define k before using it. So at the first part of our video, we defined k to be equal to k naught times e to the time activation energy over RT, right? So from that Arrhenius equation, I'm just going to define k. So k is going to be equal to k naught times numpy exponential. So we already have E over R value, so I'm going to make E over ER, and it's divided by T. Okay, so now we can return to differential equations, and we just have to make sure that we have them as an array. Okay, so we're gonna use square brackets. So let's just write everything here. So the right hand side of our first differential equation. So it's gonna be Q over V, right, times concentration of A going in minus concentration of A going out, minus K times Ca, which is going to be our rate of reaction. Okay, so this is the first differential equation. So now we have our second ordinary differential equation that we have to return. So I'm going to just write this down. So it's going to be Q over V, right, times, so the temperature going in, right, and minus temperature going out, which is going to be equal to T. And negative, as these are both negative, I can just write them as positive, right? So it is going to be positive HR, right, times K times concentration of A divided by rho times heat capacity, right? And it's going to be negative UA, right? Times, it's going to be times temperature. Oh, here I made a silly mistake. It should be T cooling. Yeah. So I'm just gonna correct it now. So we should have it as T cooling. Okay, so it's gonna be T. So T minus T cold, TC, and that's gonna be divided by rho. It's gonna be divided by rho times volume times heat capacity, right? So now we have our right hand side function. Let's just run it. So now we can use our solve IVP to solve our two differential equations. So it's going to be solve IVP, right? And so every time we're using solve IVP, the first thing we need to do is to provide the function. So we have our right hand side function, and then we have to provide t, which is going to be the time interval. So it's going to start from 0, right? And it's going to go until the t end, which we defined earlier. Then what we should give is the y0. So we should give our initial guesses. As we already have our initial values, we don't have to guess it. We can just use our not values here. So it's going to be Ca, concentration of A initial, and temperature initial, right? So this is going to be our initial, not guesses, but our initial values. So for the method, we're going to use the Radu method. Yeah, I think this is the correct spelling. And we also include that it's going to be, what? It's going to be dense output to get to be true, right? Okay. If we run this, we're gonna have our solution for the differential equations, and it is here. So we should get that. We're gonna isolate that. So we're gonna get only the solve value, and we're gonna make this equal to what? We can just make it equal to solution, okay? And run it again. So now we have our function that solves our differential equation. Now what we're gonna do next is we should solve our differential equations for a very big number of times. So let's just have our times for plotting purposes. So it's going to be and plot linspace. So it's linearly spaced numbers starting from 0. They're going to go until the end time, and we can have kind of 500 numbers, let's say 500 times. And let's just try to use our solve function for each of the values in t plotting purposes. And we can kind of unpack it right here so that we can use it while graphing, plotting. Okay, run it. So now, if I just use CA, I should be able to get all the answers. So now let's just plot it using plotly to see what is actually happening with our model. So we're gonna create a figure and make subplots. And so we have to create two plots, right? We have to plot our concentration of A respect to time and temperature respect to time. So what we're going to use is we're going to use subplots. So what we're going to have two columns, and one row. So we can have our two functions next to each other, two plots, sorry. Okay, so we created our figure, so let's just use our scatter plot, add scatter, to actually plot it. Okay, so for our x values, it's going to be t for plotting purposes, right? And for our y values, let's just have our first to be the concentration of A. And for mode, we're going to have lines. And so we should define a kind of coordinate for this. So it's going to be in row number 1. So it's going to be row number 1 and column number 1. So let's just copy everything. And for the second plot, it's going to be our temperature values. In the y-axis, it's still going to be mode's going to be lines, and for it's still on the first row, but this is going to be in the second column. Okay, let's just run it. Okay, here let's just kind of zoom in our screen to see what is actually happening. So now we have our concentration of A, the model for concentration of A, and a model for temperature. So which means as we decrease the temperature, the concentration of A is going to be increasing until a specific point. Okay, so actually this is what we needed as an answer for the first case. We also have our second case where our cooling temperature goes from 300 to 305. So let's see that if it's gonna have a different answer. So to see that what actually happens with the model. Okay, so it's gonna be 305. So we're gonna run everything. Oops, oscillations. Okay, let's decrease the end time. Let's have it at 10 seconds to see it more clearly. Okay, so we have our oscillations. So this is the thing. This is the weirdest part of the exothermic reactions, because as the reaction goes, it will generate some heat, which is gonna affect our rate of reaction. So as the reaction goes, it will generate some heat, right? So the generated heat is going to increase our rate of reaction, which means the concentration of A is going to decrease until there's no more enough to produce an energy to continue it. So it's going to go until that point where the reaction starts to go again, until this point where it starts to generate heat again. So it's going to be constant oscillations. And we cannot really control whether our reactor will kind of explode or not. So here you might say that increasing only 5 degrees is not going to make a big difference. But as our reaction is exothermic, it's going to make a very big difference. So it's going to cause a big oscillations, which we don't want to happen. So this was the video for our example problem with continuously stirred tank reactors. And so we use our two differential equations with respect to concentration of A and temperature to model our situation. And we saw two cases where the cooling temperature was first decreased and in the next part increased, and we wrote a Python code that will generate a model for our question. So thanks for your attention.